Welcome.
Hello, everyone, and welcome to the Scale in Ethereum 2024 RISC Zero workshop, ZK coprocessors, on-chain identity, and more. What you can do with RISC Zero. Joining us today are Paul and Austin, who will be taking us through this session. And with that, I'll pass it over to Paul and Austin to get the session started.
Awesome. Thanks for the introduction and thanks for joining us. Um, let's go ahead and just dive straight in. So what we're going to be talking about today is what you can do with RISC Zero, and in particular, I guess, what you can do with RISC Zero in order to win prizes for the ETH scaling hackathon. So in a nutshell, RISC Zero lets you make ZK proofs about anything you want. And it lets you verify those proofs on chain. So that's the TLDR elevator pitch. You can make proofs about anything and you can verify those proofs on chain. And what that means is that your on-chain applications can be substantially more complex than was previously possible. So let's sort of dive straight into the prize conversation briefly. We're offering 3 bounties. One of these is a ZK coprocessor bounty. One is a ZKVM application bounty. And the third is an on-chain identity bounty. So we'll talk about these in more detail as we go. But before we kind of go into the details of the bounties, I wanted to just unpack a little bit of terminology that's present so far. What do I mean by ZK coprocessor? And what do I mean by a ZKVM? So let's start with this term ZK coprocessor. This is becoming somewhat of a buzzword, and it may be already familiar to many of you. A coprocessor lets you, it's a sort of companion processor. So in this context, the EVM is the main processor, but the EVM has some limitations. You have to pay gas, you have call data limits, and the ZK coprocessor sort of framework is to say, hey, how about instead of doing everything on chain, how about I use some sort of off-chain computation to supplement my main processor, the EVM. So I'm going to repeat the words that I said at the very beginning. RISC Zero lets you make proofs about anything and verify those proofs on chain. And that's really what we mean when we say a ZK coprocessor, is that you get to have more complex applications because of this sort of power of ZK. So let me give a little bit more of a visual picture of how this actually works. Bonsai is our proving service. So here there's sort of a 4-step model for using a ZK coprocessor. You're going to have an off-chain application that's going to request a proof from Bonsai. Bonsai is going to return the proof to your application. Then that proof is going to get published on-chain and then verified on-chain. So that's the process here. Let me pause at this point and invite any questions so far about what I've just outlined, sort of conceptually about this coprocessor model. And I can't see the chat. So Austin, maybe if there is any questions in the chat, you could maybe read them out loud for, looks like we're
Yeah,
good
we'll
to,
do. I don't see any right now, though.
okay, cool. So in terms of actually like getting your hands on this, we offer a Foundry template that makes it really easy to get started with building applications that use this kind of coprocessor framework. So there's a kind of quick start instruction that will initialize a initial project, and the project will have 3 components: a ZKVM program, an app contract on chain, and then a publisher app, which we sort of saw in this diagram. Those are the components here. So the ZKVM application is the thing that Bonsai is going to run for you. That's actually what's going to get proven So the ZKVM program is what gets proven. The app contract is the on-chain part that handles the receiving the proof and calling the verifier. And then this publisher is the off-chain part of the application, which manages sending the request to Bonsai, receiving the proof back from Bonsai, and getting that proof onto the blockchain. And it's maybe also worth unpacking, like, what do we mean by a ZKVM? So I'm going to kind of briefly run through an orientation to, here's a basic virtual machine, a non-zero knowledge virtual machine, like a regular old virtual machine. You have a program that you're running, you have some inputs to that program, you run it inside the virtual machine, and you get some outputs. In the zero knowledge virtual machine framework, you have the same conceptual perspective, but instead of just getting the output, you also get a proof of that output. And the output and the proof is packaged into an object we call a receipt. So a receipt from RISC Zero serves as a proof of computation as well as the output of that computation. And in thinking about using ZKVMs, there are a number of kind of important features that you're likely going to want. One is you probably don't want to have to write all of your own crates for all of your own primitives. The ZKVM supports importing arbitrary Rust crates. So if you're trying to make a proof that involves some sort of proof of about a JPEG file or a JSON file or an EVM transaction, you can just import the relevant Rust crates and get straight to building. And then the other three features on this list are ones that are quite hard to find outside of RISC Zero ZKVM. In order to enable on-chain verification, or in order to enable proofs about really large computations, or in order to enable proofs about other proofs, requires a whole bunch of engineering. And RISC Zero has kind of already solved all of these problems. So the complexity of what you're able to do with RISC Zero is really quite high. You can make proofs about proving entire Ethereum blocks, like proving the correct construction of entire Ethereum blocks. And you can also verify other proofs easily inside your ZKVM applications. So quite a flexible framework for building. Okay, let's come back to the prizes conversation and just give a specific introduction to each of our three bounties. So again, there's three of them. There's a coprocessor bounty, there's a ZKVM application bounty, and then there's a bounty for on-chain identity applications. So the ZK coprocessor bounty, we offer this Foundry template that makes it really easy to get started. And what we're looking for here is some sort of coprocessor application. So that means that there should be something that is, if you weren't using RISC Zero, you would have to try to do it all on chain. But because RISC Zero offers a coprocessor, you're able to make your on-chain application simpler by leveraging some sort of off-chain computation. So this is quite an open-ended bounty. There's lots of different things that you could decide to build with this coprocessor model. You might think about trying to run an order book on-chain. You might think about some sort of on-chain gaming application. We recently added a library for making view call proofs, so proofs about state on Ethereum. And we'd really love to see some projects that make use of this view call proofs library. So that's a little bit of a, I guess, like bonus points for your project if you decide to leverage this view call proofs. So I think I'll ask Austin to say a little bit more about the view call proofs library in a minute. but I want to just sort of walk through the other two bounties before we get into that. So our second bounty is really open-ended. This is anything you want to do with the ZKVM. So if you're starting out with this one and finding it to be like, this is maybe actually a little bit too technically difficult for me to thrive in, this second bounty is a little bit of a lower entry point. So doesn't necessarily need to involve blockchain. We're just looking for an interesting thing that you want to make proofs about. So at RISC Zero, we really do see ZK as both important for blockchain applications and non-blockchain applications. And we're curious to see what's on your mind about ZK in general. And then our third bounty is leveraging this. We have two demos recently that leverage the fact that you can verify proofs about identity in a way that lends itself well to blockchain applications. So we released this demo called Bonsai Pay, I think in November last year, which lets you send Ethereum to someone's Gmail address. And the only way that they'll be able to claim that Ethereum is by producing a JSON web token that's signed by Google that verifies that they actually do own that email address. So this is not just for Google identities. We also have this ZK KYC demo that leverages the same sort of architecture. Basically, if you're building something, if your identity system uses OIDC, then it's going to be very direct to leverage this. But we're also open to seeing other types of identity applications here. So we're making a kind of invitation to base this off of the Bonsai Pay and ZK KYC demos, but we're curious to see what other ideas you have. So that's kind of my initial ramble. I want to pause and see what questions y'all might have, and then pass things off to Austin for a little bit more of a hands-on conversation about some of the stuff.
Also, yeah, if anyone has any of these bounties, if anyone specifically is interested in one of these in particular, it'd be great to know, because then I can, go more in detail and try to get you set up to getting started with that specific one. Otherwise, I can just go more in detail around, all of the different concepts that Paul talked about. So yeah, I'll just give a second for people in the chat to share any preference. You call, perfect. Yeah, that one's an interesting one to chat about. Yeah, what does a view call? Yeah, so I guess yeah, I can start sharing my screen and then just start talking about like what view call is. Before I start diving into some of the code and explaining the concepts, can you guys see my screen? Is everything visible? Like, is the font size big enough to be able to read the code once I start digging into stuff? I'll open the chat just to see. Okay, perfect. People can read this. So yeah, so a view call. So a view call is very, like, if you're familiar with Ethereum view calls, that's exactly what we're leveraging. So if you're not familiar with what view calls are in Ethereum, it's essentially a way to interact with a contract without actually modifying the state. So a transaction is usually one that's going to, like, you're going to send a transaction, you're going to sign it, and it's going to modify some state on Ethereum. And view calls are essentially like the GET requests of Ethereum. So it's essentially a way to perform some execution or to retrieve some data on chain without actually modifying any state. And what this view call library does in our case to make view calls provable in a ZK context is essentially to walk through this example. So for this example is in the RISC Zero Ethereum repository. So there's a few examples based on ERC20s, and essentially what it's doing is you're going to point this like view call library to an RPC RPC provider. And essentially what it's going to do is retrieve all of the state needed to perform the view call. It's going to generate a Merkle tree of the nodes that are required to access the state you're actually interacting with. And then it's essentially going to pass that into the ZKVM. And then in the ZKVM, it's actually going to perform the computation to verify that it was actually done correctly. And then it's going to commit to some essentially like the block commitment, which is going to be like the block hash.
Austin, can you zoom in a bit? There was somebody asked to zoom in.
Yeah.
Cheers, thank you.
Is that better? I mean, yeah, I can make this. Yeah, I just make it really big just to make sure that everyone can read.
I think that works. Yeah.
Okay, cool. Yeah, I'm just going to read the comments before I continue. So you have a proof every time you make a view call. Yeah, so you can generate a proof anytime you make a view call. Obviously, in the traditional context, if you just want to like view data on chain, you can just do that without generating a proof of it. But what we're providing is a way to verifiably prove that some computation will be expensive. Then it'll be expensive, but it unlocks different use cases. Like for example, say you want to be able to perform some computation to like verify that, say, for example, like you want to perform some analysis on what is actually on chain. So essentially you can do all that computation off chain so that you don't have to do it within the EVM, which some compute in the EVM is expensive. So yeah, like there'll be a lot of use cases where that would unlock. And yeah, like as Paul mentioned, you can generate a single proof for many view calls. So you can essentially roll up any arbitrary amount of computation within a succinct proof, which is just like a cross 16 at the end of the day, and that'll verify and create any assertion about any arbitrarily large amount of. Does that answer that question, or was there a specific when you were saying it's expensive, like expensive in what context, like expensive in the sense of like which metric specifically? Okay, cool. That does answer the question. Yeah, so it is obviously more expensive, but it does allow you to do some computation on verified Ethereum data. So yeah, the reason it's actually verifiable is because, as I mentioned, you're proving the actual state access is up to a specific block commitment. And then what you can do if you're posting that proof back to Ethereum is essentially check that block commitment against the block at that height to make sure that the hash actually matches what exists on chain, just to make sure that there's no invalid state there. So yeah, so just to give like a high level of this example, so this is right here. This is the host. So when Paul was talking about like the host and the guest, this is essentially what is running the ZKVM, right? At least like setting up the processes to do so, and then the guest is the actual like program itself that is going to be accepting the input and generating the actual proof. So what the host is going to do is it's going to basically point to the RPC. It's going to generate the view call and basically fetch all the state to generate the proof. Generate the Merkle proof to be able to actually do the view call. It's going to pass that all into the ZKVM, and then the ZKVM is going to basically do that view call inside of the ZKVM, so you have a proof of that computation. And then, yeah, so essentially here it just provides you with the commitment, and then from here you can either use that on Ethereum or you can use it on any chain. So you're basically proving that you did some computation relative to a specific block on Ethereum, but you don't necessarily need to verify that on Ethereum. You could verify it on any chain if you want to do some like interop use case. Like say, for example, you want to prove that you've maybe locked some tokens on Ethereum. You can essentially create a proof that you have a certain amount of balance that's locked within either an escrow or some bridge contract, and then either unlock it or mint some tokens on some other chain. So that's one option of what you could do there. And then yeah, just to walk through the guessed a bit. So yeah, so this is where it's actually like pulling the input from, like basically pulling the Merkle tree proof to be able to perform the execution and the inputs. And this is essentially where it's going to actually execute the view call, and then it's just going to return what the actual balance was. So all the instructions for how to actually run this and everything is all in the README. So if you just follow the README and go through how to set everything up, picking an RPC endpoint, all that kind of stuff. But it's as simple as just like opening the example and then just running like cargo run release with some RPC endpoint. Some RPC endpoint. And then what this will do is basically build the guest and then basically execute all this. I'm just going to, I see a few questions in the chat, so I'm just going to come back to these just to make sure I'm covering everything. What is the best point of entry to use RISC Zero if I don't know Rust? Manage to learn only basics during this hackathon. So the easiest way to use the ZKVM right now is to write Rust. I will say that the amount of Rust that you have to know is very minimal. Like you don't need to do anything very complex. It's just as much as like writing basic logic for a program. Yeah, I mean, depending on which language you usually use, there is options for what you can do to write languages, like write code in other languages. So maybe if you suggest like what is your language that you normally use, and I can maybe provide a suggestion. But yeah, I'm going to answer some of these other questions. So how do we verify on Ethereum? Is it similar to Groth 16 verification on chain? So yeah, good question. This is what I was talking about before with the, or at least Paul had kind of mentioned this with the Bonsai Foundry template. So this template basically is all like the framework enabled to be able to verify. Let's see if I can open this up just to actually show the code. So yeah, the actual Bonsai Foundry template is the one that you want to use if you want to actually post the proofs back to Ethereum, and then you can use the view call library with this as well. What this is essentially going to do is it allows, like, as I think Paul had already kind of shown the graph of like how this actually works, but essentially it allows you to, it has all the like the framework set up such that it has the contract set up such that it's actually verifying the receipts. So it's got all the templates set up such that it's got the contract on Ethereum. It's got the guest and the host all set up such that you can just write your application logic. And what this can do is basically you're posting some contract, you're basically deploying some contract on chain, and then you can verify your proofs with just like a single CLI command. All the instructions are in the Bonsai Foundry template, and I think all the links should be on the actual like bounty description. But if they're not, just message something in Discord, and we should be able to get you any links to anything or help clarify anything. Okay, I see a few more questions. I just want to make sure I touch on everything before we end here. So yeah, people are mentioning the languages they're using. They want to use are TypeScript, JavaScript. Yeah, that's a bit of a trickier one because traditionally it's tough to have those languages run inside of a ZKVM. I'd say like, yeah, there's no stable way to do that. But I will just prefix with saying like the actual code that you're writing for these applications will be very simple. You don't actually have to do any of this stuff manually. Like you don't actually have to work with Merkle trees, anything. The view call library will handle all that for you. You just basically need to define which function you're calling and how you're calling it. And the templates that we have set up should get you 80% of the way there. And if there's any questions, like we're happy to help kind of resolve those things. Let's see if there's, let me try to make sure to touch on any other questions. So can you use APIs directly in Rust without going off chain? No need to use chain-link functions and contracts, right? APIs directly in Rust without. So I'm a little bit confused by this question. When you mean without, through, off-chain, no need to use chain link functions and contracts? Yeah, I'm a little confused by this. Do you just mean like you don't have to use their oracles for data? Like whatever's on chain, you're able to basically interact with. So whatever you can perform a view call on in a traditional Ethereum sense, you will be able to essentially make a zero knowledge proof of that view call that it was done correctly up to some block hash. I don't know if that answers that question. If there's more clarification, I can answer that. To what extent are Starks used in the ZKVM? Paul answered that. Yeah, so it's basically the proof that's being generated is a Stark that can be wrapped into a snark to be able to verify on Ethereum, feasibly, because verifying Starks on Ethereum isn't feasible right now. Why we can go a little over time too. Okay, cool. I'm just gonna try to make sure I answer these questions. How much ZK knowledge is expected to know when touching this? Very little. So we should abstract all of the concepts. You shouldn't need to, like, you're not writing custom circuits or anything. You're just writing RISC code. The only thing you need to know is just like the general pattern of what ZK is and like what you're doing to make sure that you design your application correctly. But you're not writing custom circuits. You don't have to know how the Stark proofs are generated. You don't have to know how the snark proofs are generated. You just have to kind of understand at a high level, like what's actually happening and what benefits you get. And the main thing that you're targeting when creating these applications is that you want to target either something that is privacy preserving. So something in the case of, like, as Paul mentioned, like verifying job tokens, like you want to keep some information private, which can be useful in some contexts, because you don't want to, if you're verifying that you have some email address, you don't want to have to share all of your other personal data, or scalability use cases. So if there's something that you can't necessarily do on chain because there's compute limits or whatnot, and you want to basically offload compute off chain, create some zero knowledge proof of it, and then just have the result posted back to Ethereum, that's kind of like the second main use case. So hopefully that answers that question. So the ZKVM allows us to write Rust instead of designing R1CS, QAP, and writing our own circuits. Yeah, exactly. Yeah, exactly. So you're just writing Rust code that compiles down to RISC-V bytecode, more or less. And then that bytecode is basically used in the ZKVM to generate the proof. Yeah, I agree. Yeah, so I think I touched on most of the questions. I think there was one I was going to follow up with it just because I was asking some clarifying questions on. So if there's any other questions, I'm happy to answer them. But yeah, the templates that are linked in the for the bounty should have, like, the README should have all the explanations on how to get started with all these things. But if there's any final questions, I'm happy to answer those now. But it seems like I've touched on most of these. Paul, do you have anything else you want to add to this? Kind of rapid firing a lot of that stuff.
No, yeah, I think that you did a great job answering all of those questions, and it seems like the question stream is either on a lull or done. So I threw a link to our Discord in the chat, and I guess we can probably get the slides up on the YouTube description, hopefully. We'll see.
Yeah, and if anybody has any last questions, please feel free to take yourselves off mute and ask or type in the chat.
Yeah, actually, I would like to, echo that invitation for oral questions if anybody wants to jump in.
It was definitely really active, so that's good.
Yeah, and if any answer wasn't, enough detail, I'm happy to clarify any of the things I said. I was kind of answering a lot of those questions quickly.
And yeah, if you can't think of anything now, then definitely feel free to reach out to the team on their Discord channel or in our partner Discord channel as well, just to make sure you connect your hacker dashboard to Discord, so you are able to access the Scale and Ethereum specific channels. But yeah, there are no other questions here. Paul, Austin, thank you very much for the great workshop. I think you definitely got a lot of interest with folks here, so that's good. And thanks again, everybody, for joining. We've got one more workshop later today, And as a reminder, tomorrow we've got team formation sessions and the hacking begins on Friday. So take advantage of this time before hacking begins. Cheers, everybody. Have a great rest of your day.
Thank you.
Thanks all.